This is section 15.5 on chemical shift in NMR spectroscopy. So we talked already about number of signals, but now we're going to talk about the chemical shift, which is the relative placement of the signals that we observe in the NMR spectrum. So the chemical shift is typically called delta. And the reason why it's called delta, the Greek D, is because it's actually a difference measured compared to the signal observed for a reference compound, tetramethylsilane, shown here in your book, TMS. It's 4 methyl groups bonded to a silicon. In practice, this is always set to 0. Now, delta can be found by simply dividing the shift from TMS, again, tetramethylsilane, in hertz, which is a frequency, dividing that number by the operating frequency of the instrument in hertz. So if you have benzene, it will have a resonance, some signals at 2181 hertz away from TMS in a 300 megahertz instrument. So 300 megahertz times 10 to the 6th, which is million for hertz, to cancel out the hertz on top, gives you 7.27 times 10 to the negative 6. This is the parts per million number we read in the spectrum. The really cool part, well, the reason why it's a parts per million number is because this is 10 to the minus 6. Parts per million means literally 1 part for every million parts. So you could imagine the 1 part was divided by 1 million. So if you have 7.27 divided by 1 million, that is this number. The really cool part about ppm and NMR spectroscopy in general is that even if you have NMR spectrometers of different magnet strength, so 300 megahertz represents a pretty strong magnet, but 60 megahertz here represents a pretty weak magnet. Now, a 60 megahertz magnet measuring benzene will measure its shift at a different place. However, when you do this math equation, the same number comes out, showing you that the ppm number remains the same. So the ppm number, the chemical shift, is the same for every chemical on every magnet, so long as your reference is the same. Now, what's interesting is that on a spectrum, you have 2 distinct regions. From about 5, maybe 4 to the right towards 0, we call it upfield. From around 12 to 4 or so, we call that downfield. Really anything that is a higher number or going left on the spectrum, we call that a downfield position, and anything to the right or to a lower number, we call upfield. It's really all whatever your reference is. If you're talking about this shift here at around, or this peak at around 2.5, you know, it has several peaks that are more downfield than it, but it also has some peaks that are more upfield than it. So this downfield upfield is a way that we can talk about what side of the spectra certain shifts are at. Okay, so it's not super useful to know where these came from, just know that this is how we talk about them. And if protons are more shielded, meaning that there is more electron density around them, then they will get an upfield shift. And as electron density goes away, they will get a downfield shift. All right, so the reason why is somewhat due to inductive effects. The inductive effects are pretty strong, meaning if there's a molecular dipole, such as in these very simple alkyl halide molecules, then we're going to see a big difference in the chemical shifts of the protons that are attached to the carbon. Now, here the book gives you a very nice series where methane, all the protons are chemically equivalent and their resonance is at 1 ppm. However, as the electronegativity increases, that is, as the dipole moment gets stronger, the carbon becomes much more partially positive and the hydrogens then become de-shielded, meaning that electron density has been taken away from the carbon, and so they have been de-shielded from those carbon's electrons. So because this happens, they feel the magnetic field of the spectrometer even stronger. And so since it takes more energy to excite these protons, then they go downfield. So fluorine is the most electronegative element. It has the most downfield shift. And adding halogens or electronegative atoms, it kind of adds to the downfield shift we see, where in methane, again, it's 1 ppm, but adding 1 chlorine gives you 3 ppms, 2 around 5, and 3 around 7. So this is around a 2 ppm downfield shift for every chlorine added. These effects are additive in every spectrum, more or less, so you can expect the same no matter what molecule we're talking about. While these dipole effects govern the alpha carbon positions, they don't really extend past the alpha carbon. Because you see here in this 1-chloropropane molecule, the alpha carbon's protons are shifted to a much farther downfield position, but the beta protons are not. They're only about 1.6, and the gamma protons aren't really touched. And we can compare these numbers to the well-known numbers for what they should be here, where methine with only 1 H is about 1.7, methylene with 2 H's, as we saw here for the beta position, it should be about 1.2, and methyls with 3 hydrogens should be about 0.9. So you can see that the beta position did change a little bit, but nothing compared to the alpha position here. There's almost infinite types of proton chemical shifts that we can have in molecules, so I'm not going to ask you to memorize all of them. Perhaps just a few are very important, or even just a conceptual understanding of how these things are shifting, how these spectral signals are shifting. For instance, carbonyls add a little bit to they induce a downfield shift because, again, of the de-shielding of the protons. Oxygens also de-shield protons because they have a much stronger dipole induction. And then oxygen of an ether doesn't have quite as strong as the oxygen of an ester because there's not so much induction. Because in an ester, the oxygen also has resonance that contributes to the induction, and in an alcohol and ether, they don't. There's a nice resource, again, that we can look at from Michigan State. Let's show that. And in this resource, which I will post to your announcements on Canvas, the proton shifts of methyl derivatives can be shown or can be observed here, where if you have methane, again, you have around 0.9. TMS, which is a less electronegative silicon, you have around 0. Phosphorus has a very similar electronegativity to carbon. It has shift of 0.9, but as you increase electronegativity, from nitrogen to fluorine, you can see again those protons becoming de-shielded and the shifts moving downfield. And you can see a complete table here of ClBrI ethers and thioethers changing the chemical shifts of the protons based solely on the electronegativities. And all around the web, you can see very nice charts kind of like this one that show you where certain chemical shifts should be. So whether you have alkanes from around 0 to 2, or whether you have alcohols from around 3 to 4, you can find that chemical shifts of almost all molecules fall around the same regions, because inductive effects, while strong, have a limit for sure. So there's only so much shifting that can occur with simple one atom changes. Right. One peculiar thing that happens in NMR spectroscopy is what's called ring anisotropy. Ring anisotropy. So if we look at anisotropic effects, this is an effect that has a difference based on spatial positioning. If we look at certain pi-bonded systems like benzene, in benzene you have a flat ring of 6 carbons with a pi face on top because all of the carbons are in conjugation, and a pi face on bottom because of the nature of pi bonds. You have one pi cloud in one plane and one pi cloud in the other plane. Now, because you have the electron density in these two clouds, a magnetic field is generated around the ring such that it kind of goes around and then through the center of the ring. And because this is a magnetic field that's generated, the protons on the outside of this ring are going to feel like the magnetic field that we apply in spectrometry, or the NMR spectrometry, is actually stronger than it really is. So because these protons feel like the signal is stronger, they are going to be downfield. They're going to appear de-shielded, just like protons next to highly electronegative elements. And this means that if we look at a spectrum of ethyl benzene here, each of these protons is now around 7 ppms, compared to the two alkyl shifts around 1 and around 2.5. And what's key to see here is that it's not just the protons on the outside of the ring that are affected. The protons on the alpha carbon here are also affected, because instead of these being around 1.4 like we expect, these are now around 2.6, which is a very large shift, and indicates should indicate to you how the ring current can de-shield both alpha carbon protons and ring carbon protons. One fun little tidbit is that if you can somehow put protons in the middle of the ring, such as in this 14 carbon ringed aniline, where the outside is completely aromatic, just like in a regular benzene, each of these 4 carbons has a very upfield shift to -1, even more upfield than TMS, while the outside of the ring has a shift that is around 8 ppm. So the differences here are huge, and that's because of the anisotropic effect of the ring current. That's what we call this magnetic field that's generated. We call that the ring current. So some very handy chemical shifts that you need to know are shown in table 15.2. I recommend all of you to know at least all of these, because these are the most common shifts that we will find in NMR spectroscopy. And this has been section 15.6.